for x given by this function of u and v, y given by this function of u and v on the u versus v, and often this is v versus u. Kind of reverse my coordinates here, but it could be listed in either order. For an interval here of dimension delta u by delta v, we get first two corresponding vectors defining a corresponding parallelogram, and the area of that parallelogram is the area that we get when we transform this rectangle in the uv space into xy space. The vectors bounding the parallelogram are easily found by considering the change in u, the effect of the change in u on the position in the x and y plane, using the x partials, the partials of x and y with respect to u, building up this vector, and doing the same thing with the partials with respect to v, building up a vector that corresponds to the delta v on this increment in uv space, a vector in xy space corresponding to that displacement. These vectors are generally given by ru delta u and rv delta v, where big R is a vector function of x and y, x being given parametrically by u and v, y being given parametrically also by u and v. The area of this region is the cross product of these vectors, which is the magnitude of rv cross ru times delta u delta v. The magnitude of rv cross ru is the factor by which the area here is magnified when we get over here. In addition, if delta u and delta v are very small, then this region will correspond very closely to the region that would actually be mapped if we mapped all the points of this region onto the xy axis using this transformation. And all the other regions here would map onto regions of similar, not necessarily similar shape. As u and v change, the directions of these vectors are going to change, and the shapes of these parallelograms are going to change. Straight lines here are not going to give you straight lines here, so that these straight line boundaries here become curves in the xy plane, and straight lines in the xy plane would become curves in the uv plane. Now, since we've focused on a region whose lower left hand corner is pi over 3, 1, and we've actually calculated the explicit vectors, let's calculate this explicit area. Okay. All we need to do is take the cross product of these two vectors. So we have negative square root of 3i plus 1/4 j delta v crossed with I plus square root of 3 over 8j times delta u. We're going to want the magnitude of that cross product. Without going through the details of calculating the cross product, simply note that the I component times the I is going to give us 0, the j times the j is going to give us 0. Only the I times the j and the j times the I are going to give us components. Both of those will be in the direction of the k vector, out of the xy plane. So that the magnitude of this vector is going to be the square root of the sum of the squares of those k components. I'm not going to bother to use the right hand rule and determine whether the k components are positive or negative. Actually, never mind, I have to do that. I appear to be kind of talking out of my head here. Okay, so let me fix this and then we'll come back. Okay, I should probably write these out before I do them. It would probably save me time and make everything smoother, but I think it's kind of important to watch me think through the process and see some of the nuances of the solutions, even if there are some errors here and there. Now, j cross I is negative k, so from this term and this term, we're going to get negative 1/4 k. From the I term here and the j term here, I cross j is positive, but we've got a negative here. I plus j is positive k, so we're going to have negative square root of 3 times square root of 3 is 3, so we're going to have negative 3/8 k from this product. And of course, negative 3/8 and negative 1/4 is negative 5/8 k. So we're going to say that the magnitude of this cross product is the magnitude of this, which is the magnitude of this, which is 5/8. I'll note that even though each of these vectors is longer than the delta u or delta v, in other words, this vector is longer than delta u, this vector is longer than delta v, they are so close to 180 degrees apart that they give you actually a very thin parallelogram, so that the area is less than delta u delta v. Talk about thinking through things. I got hung up on the cross product of these vectors and forgot my delta u delta v. We would usually put it at the end of the expression. I'm going to slip it in there, and I'm going to write it a little better here, and here I'll write it. So our delta u by delta v region has shorter sides than our region in the xy plane, but the region in the xy plane is of lesser area because of the big angle between these two vectors that define the region. Now, I'm not going to go through and formally set up a sum and a limit to an integral. Simply going to say that if we want the area of a region in the xy plane, then we would integrate this over the corresponding limits of u and v. If we have a region in the uv plane, then that could dictate the curves that bound the region in the xy plane, and we can calculate based on that original uv region. And we can say that the area of the xy region is the integral, double integral, over the uv region. Now remember, the uv region had u going from 0 to 2, v from 0 to pi over 2. This integral is the absolute value of ru du cross rv dv. And that goes from 0, if du comes first, we'll go 0 to 2, and 0 to pi over 2. And that's then equal to the magnitude, that magnitude rather than absolute value, sorry, the integral from 0 to pi over 2 of the integral from 0 to 2 of the magnitude of ru cross rv, factoring out the du dv. Now, just to be specific about what ru and rv are, we're not actually, I don't think, going to go so far as to actually do this integral. It's probably going to be a pretty challenging integral. But remember that our r vector is xi plus yj, so that ru equals xui plus yuj, and we found xu and yu here. That's going to be 2 cosine v I, and just to make sure we got it right, 1 over 1 plus u squared, and we'll make that v, well, that's times sine v, times j. Now that's written kind of small, but I believe that's the correct expression for RU. And RV equals XVI plus YVJ. And instead of looking at what we calculated, let's just do it. XV is negative 2 sine V I, and then plus cosine V over 1 plus UJ. If we take the cross product of RU and RV, actually debating about that, but that can be written down pretty easily. It's real easy to do this cross product. It's I cross J is K, so it's this times this, which is going to be 2 cosine squared V over 1 plus U. And then J cross I is negative K. We got the negative here, so we're going to have another plus. It's going to be 2 sine squared V over quantity 1 plus U squared. So that the magnitude of RU cross RV is the absolute value of this sum. Since U is positive and V runs from 0 to pi over 2, making the cosine and the sine both positive, not that it matters because they're both squared. Both of these terms are going to be positive, so we can drop the absolute value sign, at least on this interval. Now if we went into negative values of U, that could change. So as it turns out, this isn't a particularly difficult integral. There's nothing difficult in here. We're integrating with respect to U. 1 over 1 plus U is going to have an antiderivative, natural log of 1 plus U. 1 plus U quantity squared is going to have an antiderivative of negative 1 over 1 plus U. And the cosine and the sine of cosine squared and sine squared of V are going to go along with those. We can easily then substitute in U equals 0 and 2, so we get the integral with respect to U, and we're just left with multiples of cosine squared V and sine squared V. They aren't going to be the same multiples, at least it's highly unlikely they will, so we're not going to just be able to combine these and say cosine squared plus sine squared is 1, but we can do some simplification. I'm not going to go through the details of the integration, but it turns out it's not bad at all. So that what we're integrating here, this quantity here, is just going to be 2 cosine squared V over 1 plus U. Might be a little hard to read that, but you understand what I'm writing. Plus 2 sine squared V over the quantity 1 plus U squared. With respect to U, substitute the limits on the U, and then with respect to V.